This is the third talk. I put this title about 2 years ago because I thought we are very close to the answer this problem of coupled transformation and plasticity. And now we are 2 years later and we are not so close, but we are still going in the direction. And so I keep the same title, but I will show the experiments which we did along the way to understand these things. And I like there are two articles which are here. One is Molnárova et al. And one is Bian et al., which we did in last like two years, so it's very recent work. And one of them was the TEM analysis of Martensitic microstructures during tensile test. So I just said that before we looked only at the microstructures in austenite, but we would be interested how the microstructures look in the martensite. This can be done because you can use Martensitic wire, which is Martensitic at room temperature, and then hope, if you unload, that the microstructure which was there under stress will not disappear. And I believe in that. So the content of this paper is the analysis of Martensitic microstructures, how they evolve during the tensile test on NiTi wire. Yeah? This is the first one. So in that case, because we have the small grains, like 100 nanometer, so yeah, we can easily look and we can find out all variants which are in the grain. You know. So it's very nice, but even if I look into the 4 or 5 grains, there is still no reason to believe that this is kind of relevant for any grain. So because this is the basic problem with the transmission electron microscopy, you can look something, you see something, and the question is how relevant it is. So some people say the only relevant are things which you don't see in the microscope. Okay. So to solve this problem, we perform another experiment by measuring the texture. There is a beauty of this wire that if we do the X-ray diffraction, we measure on 2D detector lots of the orientation, and from that we can calculate the texture. And texture will tell us a complementary information about the orientation of the martensite lattice within the gauge volume. It will not tell us anything about the interfaces, but it will tell us how the lattice is oriented. So I will try in this third talk today to explain the results of these two experiments, which actually brought us to understanding of this transformation plasticity coupling. So this is still some understanding of the current state-of-the-art knowledge. So if you look into the literature, the state-of-the-art is such, as I discussed a little bit before, that there is this austenite to martensite transformation into type 2 twin laminates. And so even people in micromechanics modeling of martensitic transformation, they use this scheme, but as I said before, this doesn't apply for nanocrystalline alloys. So if we care only about like these pictures, they suggest processes due to transformation only, which are these three here: elastic deformation, transformation, and some twinning inside the martensite. So if we limit ourselves to this one, there should be no dislocation, there should be no defects. But if, as I said, if we look into the wire after just one cycle, or deforms lumps at higher temperature, we see a lot of defects. So in reality, if the transformation proceeds under stress, there are defects. So these people know it, and somehow this figure is a very nice figure. It was in article by Chorbury and Sehitoglu about 5 years ago. This is a very nice article with lots of nice pictures. So somebody asked me whether there is a good overview of nitinol from the point of view of mechanics. So I think this paper is one of the good. It provides good understanding. You will get the slides, so no problem with that. And
so at point C, in that.
Sorry.
At point C, in the straight curve, is it twin Martensite or D-twin Martensite?
In this figure, this is austenite, yeah. And then he has load or cool here, and this is like austenite, and using this scheme with habit plane, it goes to the martensite. And if you cool still more, you will get this twinned martensite, and if you load still more, the red will disappear, you will get only austenite, and if you unload, you will be back in the austenite.
So from B to C, we are loading as well as
heating. Yeah. Either load or heating, you will get. This is like a intermediate point from A to this. This is full. If you are in the martensite after here or full cooling.
But in the space sustained diagram, the point C is like a D-twin martensite.
A, B, C.
Yeah. Because that is the pseudo elasticity is happening. So at a constant temperature, you are applying fluid.
Now, where is D?
D is here.
Okay, well, he put here C, but and still there are twins. Yeah. Okay, in fact, in these nanograins, this is true. We see the twins under stress. Yeah. But these guys, they don't have this information which we have. So they only put here the twins because they believe that in this C point there is a lot of twins inside. So they put here such kind of laminates. Yeah. But okay, this is schematic figure. I mean, you cannot have everything in the schematic figure. Yeah. I only wanted to point out this. Okay, I will. This is just here for the people who do the actuation. Yeah. So it matters very much for the actuation as well. You know? If you do it at 200 megapascal somewhere here, so you cycle the wire electrically, it's pretty stable and everything is fine until you are under the stress 200 megapascal. When you go to 500 megapascal, slightly more, so in the beginning you will have this instability and the whole stuff is shifting. So you will have here like even in few cycle 2%, but here you have like almost 5% of plastic strain. The hot shape will shape. Yeah? And if you go more, even the amplitude of your oscillation will go down to 2% only, and it will be shifted 8%. Yeah? But still it works. So somehow you don't have to be frightened, yeah? Because even this material, you can cycle it for thousands of cycles. But it will break. This you can cycle for millions of cycles. Yeah? So this is another magic of the nitinols, that super elastic cycling only 10,000 cycles. Actuator cycling easily minimum million cycles when you keep below 200, below some level of stress, and the magic is to know which kind of stress. Yeah? They will always tell you, if they give you the wire maximum stress 200 or 150 or 300, but they don't tell you why. And so there is a very good reason why is that. Mm?
So what the previous slide implies is, if you want to load it to a higher stress level, you have to reduce the amplitude for it to work for a normal cycle. Is that what it has been done? These four graphs. Like if you want to load it to a higher stress level, you have to.
No. We are okay. This is not about amplitude. We applied 200. We applied the load, and then you cycle the temperature in such a way that it changes from austenite to martensite. The amplitude is set by the sample. You don't decide about this amplitude is set by the sample. It's little difficult to. We are always cycling. We are heating the wire above AF, and then it cools, and then we heat and cools, and you got such kind of oscillation. But what will be the amplitude? This is the result. This is the outcome of such experiment. So you don't do it. Normally people never do at such. You never do at 1,000 at 1 gigapascal. But we wanted to go to the extreme again because we wanted to analyze this kind of transformation plasticity coupling. So normally what you use is only this one, but you can use this one as well if you can live with the original shift of 7% plasticity of the hot shape, but the lifetime would be shorter because the stresses are high. But otherwise the transformation would do. The problem is with the high stress and fracture and okay, so this was more the lecture because the motivation is to develop the actuators which can take the more heavy load. So it's about the estimating this maximum stress, and this is another picture from the same review paper by Cholbury, where before the maximum stress was just beyond the plateau. Now we go up to the plastic range. So they think about the plasticity of martensite. They take from the literature the information about those deformation bands, which other people have seen it as well, and they combine it to this scheme, which is almost close to what I will be talking, but not exactly, because they are bound to this type 2 twinning, which are observed in single crystals. When the paper was published 5 years ago, there was not so much information about the nanocrystalline alloys. Now, if they draw it now, it would look slightly different. But still, again, this paper is good overview over the knowledge of plastic deformation, not just in nitinol, but also other alloys. And okay, so now I am coming to almost to our results. So we knew all this information which was introduced before, but at the same time we knew that in the nanocrystalline materials the martensite looks very differently. It looks like this is a paper by Thomas Weitz from 15 years ago when he did high pressure torsion of nitinol in martensite state, and then the grains were small, and this was the microstructure of martensite inside the grains. So in this microstructure there is such kind of very fine lamellar. This is 50 nanometers, so the thickness of this twin is just few nanometers, and there are some kind of families. There is no austenite, so there is no habit plane, but there is this microstructure, and so this is what we knew, how such microstructure looks after cooling. And now when we look at it, we wanted to know how it looks after mechanical loading. What will happen if we deform it by mechanical load? So just a little bit more in talking about these twins. So again, as I shown in the morning, this is the austenite. These are the two variants which are related with 1,001 planes. They are like this. This is the monoclinic distortion, and here this 001 compound twins are these two twins which form these families. And because you have this is one 001 plane, this is another 001 plane, this is another one, so you can have another family of two twins, and in such a way the grain is filled with Martensite variants. So this is the result of they published finally something like 7 or 10 papers about this research. And so we knew we have the wires which have such kind of microstructures, because when we looked into them we have seen it as well. And the idea was to analyze how it changes during the mechanical loading. But before I come to it, I still should say few words. So, like, we would be most happy if we can analyze this green one, because we thought here there will be no slip, but the problem is that it fractures at 13%, and there is no way around it. So we had to use the wire which will survive this critical condition, which is something like 15 or 16. So we use 15. And so the 12 wire will stop here, but if we use this, here is 18, we use 15. So with 15 wire we can go up to 50%, but we were mainly interested in the martensitic microstructures here, because here we knew it was probably too dense. And while doing this research, we have found that in fact this brittle fracture over here, it's not brittle. If we look on the wire of 14 millisecond one, which this is this D, there is an egg. So in fact the material is very plastic. It's not brittle. This is not brittle fracture. It looks brittle because when you do the experiment, and then and you don't look really on it, but when you look on it, you will find out that this is the suddenly the tensile deformation becomes unstable. It becomes localized in the neck, and because of that, so the reason for this block is the localized plastic deformation in the neck. We have very recent articles about that, but I will not speak about it now. But it is very interesting. So and also if we use, this is like 1 micron, 18 millisecond. When the grain becomes too big, we cannot analyze single grain in the TEM. So we want it as smaller as possible. And also if the grain is big, but okay, so I want to see it in the microscope, but also the foil is thick like 70 nanometers. So if my grain is 30 nanometer, I will have 2 grain on top of each other, and when looking it in TEM through 2 grains, I got mishmash. So I must have 1 grain going through. So the grain must be bigger, much bigger than the thickness of the foil. And this is fulfilled for this 15 milliseconds. So by such analysis, we decided for 15 millisecond wire to be used in our investigations. So this is now the stress strain of this wire. As I said, it is a memory wire. So at room temperature, this is reorientation of the martensite, and yielding about 1 gigapascal, and at height and at 100 Celsius there is a stress-induced transformation and yielding about at similar stress. So the first method is this electron microscopy. So you see when it's 15 millisecond wire, about 200 nanometer grain size. So I can see, if we deform it maybe somewhere here and then unload and look by TEM into the wire, I will see how the microstructure look like. Then we can deform up to the 0.3 somewhere here. Again, we see how the microstructure look like, and if we unload and heat, we can see how it looks like in martensite, but in austenite. But now, because it's memory wire, I have to do the observation at 100 Celsius, but this is also possible to do it with them. So this is the method which I will explain more how the data look like, and then as I said, you may argue that this is in this grain, but what is in that grain, and whether this is really representative for the whole polycrystal. So to answer this problem, we do this synchrotron X-ray texture evolution experiments, which I will also describe in a little bit more detail. But here we present the data in such kind of inverse pole figures. So I'm not sure if I have further slides, so I will explain it using here. The wire has a 111 austenite texture, which means that most of the grains are oriented with 111 diagonal direction along this line. So and now this is plotted by this triangle. This is in austenite, and now I am in martensite. So in martensite is monoclinic lattice. So I cannot be enough with one triangle. I have to plot all this, but I am still interested what is the crystal lattice direction along the line. And this is the experiment, the result of the texture experiment, which actually says that the crystal is oriented, some variants are oriented here, some variants are oriented here, some here, and some here. So there are like 4 poles. So if the martensite is obtained by just cooling, there are these four poles, okay? And now if I look in this state after the reorientation, so this is when you pull the wire, it's soft, the variant changes, you have oriented martensite, then this, and this will disappear. This one will remain a little bit. This will remain, but 90% of the orientations will be here, which is one particular -103 direction in the or -102 in when I take the directions in monoclinic lattice, which actually this is the experimental evidence that in reoriented martensite, practically all martensite lattice is equally oriented with some remaining here. And now more when we deform into the plastic range, into this red point, we have inside these deformation bands. So when we have deformation bands, this is now in martensite, not in austenite, in martensite. So we see that this pole go down, so the red and yellow curve disappears, and the intensity shifts here, which means that gradually the austenite lattice becomes reoriented, but this is in martensite, But as well, I see the bands in the austenite afterwards. So this is the experimental evidence that the lattice of martensite is rotated during the plastic deformation. So now I have both. I have local information from TEM and this macroscopic information from this, which evidences what happened. So now this was the overview. I don't go to the details of how the experiments were performed. This you can find. Okay, I included here. So this is. I'm sorry for the people from the engineering background, but maybe it can be explained. This is the meter rig. We put it on the X-ray beam. Then this is the incident beam, and we deform. There is the wire, and we deform on such 2D diffraction pattern. We can obtain the distribution of the diffracted intensity. So if this is the wire of the direction, so all these directions correspond to different angles. So if we have such kind of information about the diffracted intensity under different angles, and we assume that it's a polycrystalline wire, that the texture is rotational symmetric, we can reasonably assume this. So under such condition, we can obtain, we can analyze this information to obtain Paul figures. It's a lots of diffraction pattern which we perform the Rietveld analysis. So there is like 111 diffraction pattern, and we have to perform the Rietveld analysis simultaneously on all of them to obtain such kind of Paul figures, and finally the inverse Paul figures. But all this is done to obtain this information about the orientation of the martensite lattice with respect to the wire axis. Yeah, so the experimental procedure is little difficult, but very reliable, and it took us some time to master all this progress. For example, the simultaneous Rietveld refinement on 111 spectra took us really a long time, one day. So it was impossible because you can have along the stress strain curve you can have 2,000 points, and if one analysis takes one day, it will not be possible. So we had to purchase the parallel computer with multiple cores where these things can be run in parallel, and then it takes like 10 minutes, and with that we can reasonably, because this experiment here, it lasts for 2 minutes. Yeah? So we come for 5 days, we measure 200 data like that, and the time to evaluate everything would be 100 years. So we have to somehow speed it up and select what is really relevant. So the most the easy, this is the test in the martensite. Yeah? So you start with the martensite, you have reorientation until the plastic wrench. So this we did, this was already published. But now you can have many other experiments which you can imagine where the analysis of the texture would be interested. We did many of them, but we have no chance to evaluate everything because it's too much work. You know? But the method is nice and can be used to analyze the texture evolution in any material which undergoes deformation, twinning, or phase transformation. Okay, but more interesting are the results. And now it's a little bit, this is my presentation. I try to present it on some day in our institute, because my idea is that what is really interesting is the synergy of these two methods. When you have local information in grains by TEM and macroscopic information from the texture. So if you have both of these, you can better understand. So now let's go through the experiment in martensite. So again, this is the stress strain curve, and this is how it looks, the microstructure before the test. So if you you don't see much. This is because in electron microscopy, like if you want to analyze maybe this grain, you have to rotate suitably everything. And so, because the next grain is differently oriented, if you take a bright field from white area, you will not see anything. That's not possible by just taking a bright field. But still, if you do that, so if you look here, and then if you deform up to 400 megapascal, reorient or variance, unload, make the foil, suddenly you find out that many grains, you have this kind of lamellar microstructure. You know? And indeed, this is the true, because when you do it carefully, then whichever grain you look at, you will find that now each grain is filled by single lamellas of this type 2 twin. So for me, this was a big surprise, because under that last 30 years, which when I have seen a picture of deformed martensite, I always seen many different kinds of twins, some kind of jungle. For me, I didn't understand anything. Yeah? And now we look into these nanocrystalline materials, and so we have this. So this is how the diffraction pattern looks. You have, it's basically 2 interpenetrating lattices. I can make the dark field with magenta and cyan, and this is like complementary contrast. So everything is absolutely clear. This is the 001 compound twin, and this compound twin is complete domain. Yeah? Some grains, if you look into it, they will have here some kind of relict bands, but one can understand this is after reorientation. Before there was a jungle, and these kind of relic domains, if we deform a little bit more, they will disappear. You know, they were here before, and during the reorientation, the other domains were, because they provided less strains, so they disappeared, and you end up with such kind. And the important point is that we really analyzed something like 20 grains. I'm showing here only 3, but in all 3 cases, the whole grain is filled by 2001 compound twins. And now, if we look into this X-ray texture experiment, so before the experiment, we had these 4 poles, which suggest that along the wires I have 4 different types of variants. This comes from the symmetry change. So in 111 direction will change into the 4. If I have other direction like 001, it will change in 2 or whatever. Yeah? But don't be so much. So, and then if reorientation occurs, which is here, so I have 4 in the stage 2, which is here, I have also 4, and in the stage 5, which is here, next to it, because the deformation band passed through it, these 2 disappear, and I have only 2. I have only 2. Why I have 2? No, because by TEM we have seen there is a laminate, and laminate means 2 kinds of orientations. Yeah, so this evidence very nicely confirms the TEM observation that every grain is a laminate of 2 twins. And so now in stage 6 I have these 2 twins, and when I load it in 7 and 8 I still have 2 twins. Yeah? So here in this we call it like a elastic range of the martensite. It starts from 300 megapascal up to 1 gigapascal. It is almost elastic, but inside the grains there are these laminates of 2 twins. So sometimes the people call the reorientation detwinning, but why you would call it detwinning if even in 7 and 8 you still have twins? So now I say detwinning is not proper word for this reorientation. Reorientation and detwinning are different things. In fact, during this elastic range, these grains are not detwined. It remains twinned. This information is very clear. Yeah. Okay. So I have this kind of twinned microstructure. Maybe I go. Yeah. And then it deforms plastically. So when it deforms plastically, I need to go back. No. Okay, this is differently organized. So let's look at first at these pole figures. So when it deforms plastically, suddenly you see that the intensity here is decreasing and here is increasing and moves to the right. So it's absolutely clear that the plastic deformation is connected to reorientation of the martensite. Before I was talking about that when I was talking about the austenite. Now I'm talking about the martensite. So if you look into the textbook, you will find the information that martensite deforms plastically by dislocation slip. Now, well, if it's by dislocation slip, it must rotate very significantly the martensite lattice, which cannot be just due to conventional slip. So there is something different happening, and so one evidence is this kind of change of the texture, and the second evidence is from okay, I will not this is probably not necessary to discuss. So this is a good, everything is on this figure. If I click it here, yeah. So this is only for a reorientation. So I start with this kind of jungle with multivariant in grains. With during the reorientation, it will change in such a way that there is a single laminate of 001 compound twins, which provides. This is the macroscopic information from texture evaluation, and if you heat this, practically all strain is recovered, and you will end up with austenitic lattice without any defects. So this is the beautiful functional macrostructure response during the shape memory effect. No plasticity here, no these deformation bands. And now we look again by TEM into the microstructure of the wire, which was deformed up to 15%. So deform up to 15% and unload. Believe that after unloading, the microstructure which was there under stress remains in the foil after. And so now this is here, so you don't see anymore these kind of fine laminates, but you see a different microstructure, which is shown here. So now, before I have shown only schematically this microstructure, and this is the result of the analysis of the microstructure here. So now you can look into the paper to find out the details, but just to explain you to understand. So I have selected some grain here, and I already know from the analysis before that I have to rotate the foil in such a way that the electron beam is aligned with 010 direction. 010 direction is a direction along which the martensite is shortened, because when this is the wire, we cut the foil, the thin foil was cut like this. So martensite is long in this direction, short is thin direction. So if I look along the 001 direction, it will be shortened. But one thing is very now striking. If I turn the foil into the 010 direction, you know here you don't know where is the grain. You see only some bands. But when I turn it, suddenly it becomes completely black. Why it is black? Because the because the electron beam comes through and diffracts very strongly. Diffracts everywhere in the grain. Everywhere in the grain strongly diffracts, so it becomes dark, and so it means that if there are some bands, and there are many bands, the lattice is misoriented in such a way that that the 001 direction is the align with the beam in all these variants. Yeah? So it is very, very, very special misorientations of the Martensite lattice which are created by the plastic deformation. The question is why. And but now we don't search, we try to analyze this. So if you have this, so these are the diffraction patterns. All of them are in 010 direction, but rotated, differently misoriented. So to analyze this, we have here something like six Martensite lattices differently oriented. And because this is jungle and no one can understand it, I put here few pictures which concern different kind of lattices. So for example, green and red, or here cyan and blue. So like if I have blue and green, where is blue and green? Okay, this is blue and cyan. Yeah. So this is the characteristic pattern for 001 twin. Here, these are some relict 001 twins which can be found here. But by this analysis, I can find the Martensite lattices which are all rotated like that, different kind of rotations. So we can identify all misorientations which are here, and we can reconstruct these twin maps. And the way how it is done is very same. If I can if I look with maybe with this green direction, so I can see only these twins because I have two kind of diffraction. So with using different kind of dark field imaging, I can reconstruct this microstructure. Okay, you don't have to go to the details. The important thing is that suddenly in the grain I have the microstructure which was evidently created by some kind of deformation process in the material, which make it. There is no jungle. This is very nice order in it. Yeah. So some lattices are some misoriented like this, and the reason why it is that I'm nearly the end of the talk, so I have to be quick here. But some of these rotations, they provide like 20% of strain. So it's very effective straining mechanism, the rotating of the lattice. So that's why the Martensite does it, but it does it in such kind of localized manner. So to prove that this is reality, we made the high resolution analysis of individual interfaces which are here. So this is now like 10 nanometers, and we can look at different kind of the interfaces. So here there is the 001, this is this laminate, which there is the 001 interface. Another interface is here, so different kind of interfaces which are here. And so as I said, in all cases the Martensite lattices are rotated. And there is one striking thing. If I plot the traces of the 001 direction, yeah, regardless for every interface which is here, and we did it even more, you will find that there is a sort of mirror symmetry. So always this and this are in some kind of angle. It can be different kind of angle, but it's always mirror symmetry. So when I look at it, we were very surprised what do we see? We were thinking about it. I will talk more about it later, but finally the explanation of this is very, very simple. It is still the same. The material can only create the interface which is strain compatible. And of course, if you have the shape strain, some kind of like a shears, so if you imagine two sheared microstructures which should form compatible, it has to be a mirror plane. And then if you look on the traces of the 001 plane, and because this shear is always shear on the 001 plane, you can use the traces of 001 plane evidence on it, and you will get such kind of pattern. Yeah. So I will talk about that more later. This I have already explained. And yeah, I think this is not so. This is just the summary of what basically I have been saying here. There is the conclusion and some takeaway. So I am probably at the end of today's talk. Thank you very much. Yeah.